So during part 3, we're going to pick up right where we left off. We did an estimation, okay, an estimation of how many calories you could burn in a day just based on your body mass. But let's say that somebody's at rest and you have them attached to a metabolic cart and you actually can measure their oxygen consumption and their carbon dioxide production. In this case, after 1 minute of steady state sitting in a chair at rest, we've measured that somebody has produced 0.32 liters of CO2 and they've consumed 0.37 liters per minute of oxygen. So just like when we were learning how to calculate gross efficiency, we can determine how their energy consumption based on their RER, an RER table, and their oxygen consumption. So first of all, RER is going to be V CO2 produced divided by VO2. Nicely arranged, so we divide those two numbers. And in this case, we'll find that their RER was 0.86. Now, if we consult our RER table, it can tell us that that is equivalent to 4.88 kcals of energy per liter of oxygen consumed. So, in 1 minute at rest, 4.88 kcals per liter of oxygen times oxygen consumption, 0.37 liters per minute, is going to give us a total energy utilization of 1.80 kcals per minute. So, during 24 hours, we could estimate this person's total energy consumption of 1.80 kcals per minute times 24 hours times 1 hour, times 60 minutes per 1 hour. And what we'd find is that they consume 2,592 kcals per day. So in the previous part, we estimated just based on body mass. Now that we've actually measured what their metabolism is doing, okay, and we've consulted an RER table, we can see that they need to consume at least 2,592 calories a day or kilocalories a day in order just to maintain their body functions. So let's review the net efficiency equation quickly. If we want to calculate net efficiency, which we'll get to in a minute, now we have our energy derived from ergometry divided by our total energy measured by a metabolic cart during exercise. And from that, we remove the portion of energy that we would be using at rest anyway. We multiply it by 100 in order to obtain a percentage. And what I want you to remember about the percentage is that it's always going to be greater than gross efficiency. Okay? So we'll always appear to be more efficient once we remove that resting portion. So let's go through an example. If we were rowing at 80 watts for 1 minute, we have to match that so that we're cycling for 80 watts at 1 minute. And in both cases, you have to make sure that you're in steady state. In other words, we want a submaximal intensity where the majority of or almost all of our ATP is being derived aerobically so that the metabolic cart can pick up these numbers. And we're ready to make our comparison. Now this is nice because it simplifies our math. The first thing we want to do is calculate the energy it takes to do the work. So which formula do we use? We have two options, force times distance or work over time. Well, in this case, we know that it's 1 minute and we're given, sorry, correction here, power output times time. So in this case, we are given power output and time, so we're going to adopt that formula. And the power output has been matched on the rower and on the bike. And we'll do that in lab. If they're matched, then we can determine that 80 watts, okay, times 60 seconds is equal to 4,800 joules. And now if we want to convert that into kilocalories, we have to remember the conversion factor. So 1 kilocalorie is equal to 4,185 joules. That's not something that we measure, it's a constant that you have to know and apply at this stage during the equation. So times 1 kcal divided by 4,185 joules. Just use different color, our joules will cancel. And we're left with an answer of 1.147 kcals per minute. Very important number. I'm going to circle it and we're going to use that later on. Okay. In order to calculate net and gross efficiency. So now that we have the person in steady state and on the rower, we're going to collect some metabolic data. In this case, they're producing 1.53 liters per minute of CO2. And they're consuming 1.65 liters per minute of oxygen. So if we divide one by the other in order to determine RER, what we get is an RER of 0.93. So now we have to consult our RER table. I'll show you again here. And if we find that particular RER, we will see that it requires 4.96 kcal per liter oxygen. So 4.96 kilocalories per liter oxygen times our oxygen consumption. Okay. Has to be reintroduced, so 1.65 liters per minute is going to give us an answer of 8.2 kilocalories. During that 1 minute of measurement. So let's do the same thing for the bike. We hook the metabolic cart up, we achieve steady state at 80 watts. They're cycling, everything is going well. Their carbon dioxide production is 1.48 liters per minute. And their oxygen consumption is 1.55 liters per minute. We can calculate RER, divide one by the other, and we determine it to be 0.95. We consult our RER table. Okay, our RER table tells us that this is equivalent to 4.99 kcals per liter of oxygen consumed. So when we want to figure out our energy, 4.99 kcals per liter of oxygen times, in this case, we have to use the oxygen consumption we just measured on the bike, 1.55 liters per minute. We're left with an answer of 7.71 kcals per minute. So now we have all the information we need to calculate efficiency. And lastly, so when we calculate net efficiency, we're going to include the resting metabolic rate. When we calculate gross efficiency, we don't have to. So let's just do this very quickly. So the gross efficiency when we're rowing is going to equal to the energy of work divided by total energy, which is equal in this case to energy of work 1.147 divided by total energy measured in the metabolic cart times 100, or 14%. On the bike, okay, the work is the same. Now, why is that? Because we matched power output during the measurement. So when we calculated the energy, it's no different between the bike and the rower. But when we measured the open circuit spirometry, we have to use that which was measured during cycling at 7.71 kcals per minute times 100. And now in this case, we'll find out that it is more efficient, so closer to 14.9%, which is a typical finding. Cycling is usually more efficient than rowing. So lastly, net efficiency. It's very similar. Energy during work divided by total energy minus the resting metabolic rate. Okay. So let's put those numbers in. The first two are the same as before. 1.147 kcal per minute. Okay, now follow the order of operations and use your brackets because the total energy of 8.20 kcals per minute subtracted by the resting metabolic rate, 1.8 kcals per minute. Will give us an efficiency that should be higher than our gross efficiency, and it is 17.9%. Apologies, times 100 here. Quickly for here, 1.147 divided by 7.71 minus, okay, the same resting rate. Because at rest, it doesn't matter if we're going to go on and cycle, if we're going to go on and row. At rest, it stays the same. So 1.8, okay, times 100. Here, we're left with a net efficiency of 19.4%. So it's a bit complicated. Follow this example, practice it several times, and you'll be able to calculate gross and net efficiency on two different types of ergometer and calculate the resting metabolic rate.